Okay, let us give the product for the following reaction. So I will show you the reactant. So let me draw here. So 7.43. So question number 7.43 we have. So what we have, so I have a 4-member ring this side, and this side also I have a 4-member ring, and then I have a basically bridge head, something like this. This goes, and there is something like this. I think we have copied this one. And then here I have CH2OH, and if I treat this compound with H plus, some heating is also there. This means I have to write an alkene. So let me give you the final product is an alkene. You have to give me the final product. Using the mechanism you can derive the product. Basically in this case you will get a product that is not a set of product. You will get a something that is a different than set of product. So let us try to derive this product with the mechanism. What will happen in the first step? You will generate CH2 plus. Let us take some 1 minute time so that you can try. So let us try. I will give you a hint. First make a carbocation, then rearrange the carbocation and then lose H plus. Then you will get a alkene. So let us take 30 seconds time. Okay, let us see. So you have something like this. Now what will happen in the first step? You will make a carbocation CH2 OH2 plus. So let me write OH2 plus, and you will lose this one, and then you will have a primary carbocation. So you have something like this. So you will have CH2 plus. Now this is a 1 degree carbocation. What can I do next is, now I want to rearrange this carbocation. Now if you see this side I go, how many carbon we have? 1, 2. If I go this side, how many carbon we have? 1, 2. If I go this side, 1, 2. So this means these 3 rings are equivalent. Either I shift this bond, or I shift this bond, or even I shift this bond. All are the same situation. So either I shift this bond, are you getting? Or I shift this bond, or even I shift this this bond, the upper bond, we will get the same situation. No any other choice. So I have only one choice. Any bond I can shift. So let us try to shift this bond. If I shift this bond, what will be the product we will have? Let us call this 1, 2, 3. Now this carbon and this carbon will be connected. So let us call this a 4, and let us call 5. This is 6. This is 7. So let us draw between 1 and, so you will have 1, 2, 3, 4, 5. So how many ring? 5-member ring. So this side will have a 5-member ring. So let us make a 5-member ring this side. Are you getting? And this side will have a 4-member ring. And here we will have a something like this. Are you getting? So this side you have, so let us say 1, 2, 3, 4, and here we have 5, here we have 6, 7. Try to see what we have done. 3 is attached to 4. So I have joined 3 and 4. So 3 and 4 are joined. And 4, and let us say 4 is joined to the 5. So 4 is joined to the 5. 5 has two rings. This ring top one and this ring. So this is connected to the 2 rings. This is 1 ring. And this is another ring, 4-member ring. Now see, the positive charge will appear of carbon number 5. So carbon number 5, you see we have broken one bond. So it will contain the positive charge. Now here I have a hydrogen. So there is a hydrogen also. Now you see, in this case this is a very unstable carbocation because positive charge on bridge head, so this has to be sp2 hybridized. Carbocation is sp2 hybridized, but it is not possible. Geometry does not permit to have a bond angle of 120 degree. So this is very strained carbocation, very strained carbocation, very strained, angle strain. So we have a high angle strain in this case. Are you getting? Now what we can do is, in the next step, if I do a hydride shift, I have two options. I can shift a hydride from here, or I can shift a hydride from here. So if I shift a hydride from this side, I will have a double bond in 7-membered ring, that is slightly less strained. If I shift hydride from this side, I will have a double bond in 4-membered ring, that is not a good situation. So let us try to shift this one. If I shift this hydride this side, so what we will have? So this side I will have a 5-membered ring. Are you getting? And this side you will have a 4-membered ring. And here you have a something like this. Are you getting? Now at 4 you will have a positive charge. Are you getting or not? So if you remove from 4 one hydrogen, you will have 4 positive charge. Now you see, you have two options now. Here you have a hydrogen. If I have to lose H plus so that I can get an alkene. If I lose this H plus, I will have double bond here. But now once again this will become sp2 hybridized. Alkene is sp2 hybridized. So this is not permitted by the angular strain. So I have only one option. I have to lose H plus from here. If I lose H plus from here, what we will have? I will have a 6-membered ring, 5-membered ring. This. And here I have a ring. I think you have written this one. And then there is a double bond. Are you getting or not? So I will have this compound. Now see, somebody can thought that I should have make the double bond. If you make double bond here, you will have a major substituted product. But that is not the case. That will be a substituted ZJ product because you have a double bond, there is more substituted. But that is not the case, because if I make a double bond here, this carbon becomes sp2 hybridized. That does not permit. So I can say I cannot have a ZJ product. ZJ product is restricted by angular strain. So I can say ZJ product is restricted by angular strain. I cannot have restricted by angular strain. So this time ZJ product is not the major product. Are you getting? We are getting an alkene, but this double bond is in a 5-membered ring, and this is not a ZJ. This is not major substituted. So not major substituted. This double bond is not major substituted. You see, if you have a double bond here, that double bond will be more substituted. One alkyl group, another alkyl group. This also, this is a tri-substituted. Now this is only di-substituted. This side you have hydrogen. This side also you have hydrogen. So this is only di-substituted alkene. So this is di-substituted. So you see what we have done is, what are the driving force in this reaction? The first part is easy. So let us write from the top and then we slowly give down. So now see, first part is easy. I have to make a carbocation. Now I have to, this is a primary carbocation, 1 degree carbocation, very unstable. I have to rearrange this carbocation. To rearrange this carbocation, I have option. Either I can shift this alkyl group, or this alkyl group, or this alkyl group. These three alkyl groups are basically equivalent because all contains a 4-membered ring. So this is also part of 4-membered ring. This is also a part of 4-membered ring. This is also part of 4-membered. So if you shift any of the alkyl group, there is no problem. Now let us shift this alkyl group. If you shift this one, now this side, if you shift this side, so this will become, so this ring will become 5-membered. So you have to make a 5-membered ring this side. And now there is a positive charge. Now this positive charge is not stabilized because of the angular strain. Carbocation is sp2 hybridized. Now this is sp2 hybridized, but the angular strain does not permit that this angle should be 120. But that is not possible because at bridge head I cannot have a 120 angle. This is a the geometry does not permit angle of 120. So I have to as soon as this is formed, this is basically unstable. As soon as this carbocation will be formed, this will rearrange, and this will be rearranged by hydride shift. And then in the next case, if you lose H plus from here, that will not the case because double bond that is formed, that is sp2 hybridized. Once again, the angle does not permit that I can have a sp2 hybridization here, so I have to lose H plus from here. So I think if we lose H plus from here, we will get a less substituted product, that is not a set product. I think all of you have able to understand. So let us copy this one, then we will go for the next problem. Okay, I think you have copied this one. Let us go for the next problem.